Good afternoon, everyone, and welcome to today's Sculptform webinar. My name is Blake Proud, and I'm part of the team here at Sculptform, and we're very, very excited to have you guys here. Thank you for taking an hour out of your day to be with us. Today, we're going to be exploring the concept of thermal performance in facade build-out design, and we're joined by three lovely expert speakers who I'll be introducing you guys to shortly. In the spirit of reconciliation, we acknowledge the traditional custodians of country throughout Australia and their connection to land, sea, and community. We pay our respects to their elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islander people today. Now, just really quickly for some housekeeping, we're working on a platform called Livestorm. Livestorm is really great as a webinar platform for user engagement. There's a handy chat box on the right-hand side, so we encourage you guys to say, hey, let us know where you're tuning in from, and we've got a few Sculptform representatives monitoring that chat as well. But what's really important is on the top of that chat box, there's a questions tab. Now, today's presentation is going to be quite technical. We're going to, myself and Dave will be outlining some very key basic thermal concepts, and then we'll be handing over to Alex and John, who are experts in regards to thermal performance, who will be working through some technical details. So if you have any questions, we do encourage you guys to ask those in the questions tab. And just a tip there is to initial those to either A for Alex, J for John, or D for David, so that when we do the Q&A session at the end of today's presentation, we know who to ask those against. And there's also, it is a CPD presentation, so I will go through some of the CPD questions at the end of today's presentation. There'll be a survey that comes out for you to answer those if that is something that you're interested in. Now, we're joined by a talented pool of speakers today, and we're really excited to have each of those with us. The first person is Dave, who is one of my colleagues, and he's been the product development manager here at Sculptform for the last 7 years, and he's a really passionate worker behind the scenes who's actually responsible for quite a number of our innovative click-on connection products. So quite a lot of what you see on the website and all of our connections and details and whatnot are a result of Dave and his work. And Dave has a really strong focus on developing products that help bridge creative architectural design with practical buildability on site. We're then also joined by Alex George from Dynamic Composite Technologies. And Alex has a passion for building science, occupancy, and energy conservation. And those are all concepts that we'll be discussing and exploring today. Alex has spent the last 15 years concentrating his efforts in improving building envelopes and their performance. And then lastly, we're joined by John Davis from Oculus Engineering. John is the head of research and development at Oculus, where he coordinates guidance documents, studies, tests, and occasionally burns something or blows something up, which I'm sure John has all done in the name of research and science. I also know John's been conducting some research into retrofitting existing infrastructure to improve thermal performance, and I'm hoping that's something we'll learn a little bit more about a bit later today. So in terms of agenda, I just I'm going to give you guys a quick background of why we're focusing on this particular element of facade build-out design, and I'll quickly introduce a rainscreen click-on cladding product that we've been working about. Before I'll throw you over to David, who's really going to explore some of the basic principles that really will help provide a bit of a framework and some context before we hand you over to Alex and John, who will both be talking about some common build-out examples, how to improve thermal performance, and then some of the common misconceptions in relation to thermal performance. And Alex in particular will compare a couple of different revisions of the building code, so the NCC 2016 and 2019, and just update us on a few of the key changes. As I mentioned, it's a bit of a technical presentation today, so we anticipate the speaking component probably to go for about 55 minutes to an hour, and then we'll have a question session at the end. So as you work through, as it is technical in nature, if you do have some questions, we would love to answer those. Please put those in the questions tab, and we'll raise those, and any of those that don't get answered, we'll also do a follow-up email in a week or so with some answers. For those of you who are unfamiliar, here at Sculptform, we are an architectural lining system manufacturer. We're 100% Australian owned and operated, with our head office based in the lovely regional town of Bendigo in Victoria. And we work primarily with architects and designers all over the world, and we provide a range of click-on timber and aluminium modular systems for walls, ceilings, and facades. As an organization, we are really, really inspired by the direction that the design community takes our product. And that's basically the starting point of today's presentation. So to try and keep a really long story as short as possible, this entire presentation and the product that we've released recently, Click-on Cladding, is actually the result of a meeting we had with an architect going back 3 or 4 years ago. And it was in relation to a bit of a hole or a gap within our range of products, but it's something that's becoming increasingly common. And that was an architect who came to us they needed a real timber solution for a facade, but it also needed to meet Group 1 fire compliance, which again these days is increasingly common. And basically at that stage, we didn't really have an off-the-shelf product. So while we came up with a custom solution for that product, or for that project, we started on this journey about developing a long-term solution. And when I say it was really led by Dave, who you'll hear from a little bit later today. So Click-on Cladding it's an extruded aluminium product, and I guess it's a rainscreen facade, which we'll talk about some of the advantages of a rainscreen facade a little bit later on. But I think the biggest advantage of an aluminium extruded product is that you can do all kinds of different textured finishes, as well as adhering a wood finish wrap to it as well, so you get that real timber look. But the other kind of key advantage for the industry that we work in is that it utilizes the same click-on connection that the industry's come to know and love. So that means the builder understands its capabilities, architects and designers know how to detail it, they specified it before, and then installers have worked with it. It's really quick and easy to detail or to install. So at this stage, you're probably asking yourself, well, how does that necessarily relate to thermal performance? And that's a great question. And honestly, as an organization, when we started the journey of developing Click-on Cladding as a product, we really didn't understand too much to do with thermal performance and why it's important. So Click-on Cladding is a rain screen. It's designed to sit at the face or the front face of an external facade building envelope build out. But what we began to kind of learn more and more about is it's actually the componentry that sits in behind that Click-on Cladding or that rain screen product that's hypercritical. It's super critical to making sure you're designing a building that's performing well, it's energy efficient, it's durable, and it meets engineering compliance as well. So there's 5 key principles to building envelope design. There's aesthetic considerations, weatherproofing, fire regulations, thermal performance, which is what we're discussing today, and then all of the wind loadings. And I guess how that relates to today's webinar is that when we were learning more about rain screen cladding and all the componentry, we actually went out to a series of experts and we learned quite a bit. And that's where Alex and John come into play. They helped us quite a bit in developing our knowledge of thermal performance. So thank you to both of those guys. And as we were learning more about it, we basically said as a team, hey, this stuff's really, really interesting, and we'd like to share it with our clients. So that's why we're here today. We hope you guys find it useful. So just really quickly, just the key learnings for today. When you guys leave, we'd like you to be able to identify some advantages of using a rain screen in your facade design. We would like you guys to be able to identify the common methods to improving thermal performance in your building envelope. That's something we'll talk about quite a bit. And then also importantly and holistically, we want you guys to understand the importance of good building design and how thermal performance impacts operational carbon. And I think that's incredibly relevant these days when sustainability is becoming more and more of a need going forward in the construction sector. And with that, I will hand you guys over to Dave.
Thanks, Blake. Thanks for your kind introduction. This is a great topic, and just super excited to be part of this presentation today, really. So I just wanted to take a step back a bit and just look holistically at why thermal performance is so important. And what you can see on the screen here is the population growth looking back about 300 years and a projection looking forward. Just what I want to point out here was really the staggering growth over the last sort of 50 to 100 years. So right now we're sitting on about 7.8 billion as a globe, and just back in the 30s we're on 2 billion. So it's nearly a 4-fold growth, which is pretty amazing. So although, as you can see there in the purple line, the growth rate is on the sort of sharp decline, we're still expected to see a fair bit of population growth over the next 50 to 100 years. So it just goes to show, how important it is going forward that we're considering our buildings and considering the importance of carbon and improving the building sustainably, really. And it just goes to show that building is not going to stop. This population growth is going to need infrastructure to support it. People are going to need somewhere to live. They're going to need somewhere to work. So construction is not going to be stopping anytime soon. And just to move on, I just wanted to quickly chat about the different types of carbon. And there's two main types of carbon when it comes to building and construction. So the first is embodied carbon, and that's the carbon involved in or emitted in the manufacturing, the transport, and the actual installation of a building that's within the building. And then there's the operational carbon, and that's the carbon emitted over the lifespan of the building, say 50 to 70 years lifespan of the building, and that's mainly in energy usage, which with HVAC systems and lighting, etc. And on average, in Australia, about 35% is embodied in a building, and then about the rest of the 65% is actually operational over the lifespan of the building. And so keeping that in mind, about 25% of all emissions in Australia is due to buildings and construction. So you can just sort of see how important this is in getting this right, and how we can make a real difference by improving operational carbon through better thermal performance of our buildings. And today we're just focusing on the operational carbon side of things. Okay, so the reality is there is a thermal contradiction out there. Outside in the environment, we've got a lot of variability. It could be hot, could be cold, could be humid, could be dry. So, and then inside, we wanted to keep that sort of consistent, comfortable temperature, 21 degrees with a constant humidity. And really the only thing that's protecting us from that high variability is our building envelope, what surrounds what's the outside of our building. And so trying to keep that consistent temperature and humidity is going to involve, electricity and the use of air conditioning. And really what we want to try and nut out a bit today is how can we use the building envelope to try and reduce the effect of the external climate and reduce the need for electricity. So today we're talking about facades because that's what we do. Although heat can be lost anywhere in the building. Could be lost through the roof, through the windows, through the floor. So we're just focusing on facades today. We'll just move on to the types of thermal transfer. So first we got conduction heat, and conduction heat is heat transferred through a material. So that's like your stovetop, like we show there. That heat coming through the pan and cooking your food is in fact conduction heat. Then we have radiation heat or radiant heat, and that is like heat traveling through air. So for example, you've got an oven that's not with the fan turned off. That heat warming that environment is just the heat coming off the raw elements, heating that environment. That's radiation heat. And then there's convection, and that's using the flow of air really to take the heat off the elements, and it's a more efficient way to get the heat around. So all these types of thermal transfer are acting on your building envelope and working against it really. And but what we want to learn from today is how we can minimize the effect of these types of thermal transfer, and in some cases actually use them to our benefit. So just to dive a little deeper into conductivity specifically, and then into R values, which we all know. So as I said, the conductivity is the flow of heat through a material, and every material has a different conductivity rate. The timber on this desk has a different conductivity rate to, say, the glass behind me. Everything has a different conductivity rate. And then when we flip that around, we get the R value, and that's really the resistance. Keyword there is resistance to the conductivity of heat. So, so what you're looking at there is pretty scientific and complicated formula, but really the crux of it is pretty simple. To increase the R value, so the higher the R value, the more resistant it is to the heat. You either got to increase the thickness, so the heat will take longer to get through your wall type, or you got to reduce the conductivity of that material. Therefore, the heat takes longer to get through the same thickness, pretty much. Okay, so thermal bridges. A thermal bridge is really it's like a electrical shortcut, short circuit through your facade. So your heat is always trying to find the path of least resistance through your facade, and where you've got a material that is bridging from the outside skin to your inside wall that is a higher conductivity rate, that's what we call a thermal bridge. And just to the right there, you see a graphic example of what a thermal bridge might be in day-to-day life. So you got a damaged oven mitt, and your fingers protruding through the insulation. If you go and you pick up a hot dish, obviously your finger is going to feel that heat a lot faster than the rest of your hand that's behind the insulation there. So just how much faster does heat travel through the thermal bridges than through the insulation? So what you're looking at there is the section of a steel stud with insulation bats in between, and all things being the same, the heat traveling on path B or through the stud will be traveling a staggering 1,300 times faster than through the insulation bat. So we just got some fun facts there on the screen. We compared the conductivity of DCTech's Vulcan wool insulation with other commonly used building materials. So you can see their timber is 4 times higher conductivity. So it's a lot better than steel at 1,300 times, and then all the way up to aluminium, which is 7,000 times faster than insulation. All right, so what we want to try and do in a building is break that flow of heat. So the heat transferring through the wall, we want to try and break that somehow. And this is where Alex and John will dive a bit deeper into how you can do this, in reality. But just the note here is the heat is always trying to get out. It's trying to find the cold. So on a hot day, your heat's trying to get into your envelope or into your building, whereas on a cold day, the heat's trying to get out. And I just wanted to touch briefly on the benefits of a rain screen and also the thermal benefit, because there is a thermal benefit. So our Click-on Cladding system is a rain screen cladding system, and so the core parts of a rain screen is the skin on the facade. That is stopping the majority of the elements, such as the rain and the rain, the wind, and the UV. And behind that there's a ventilated cavity, and then behind that again you've got your insulation and your waterproof membranes. So if rain is hitting the facade and some is getting through the rain screen skin, the design is such that it will drain out. And what's more, because of the air movement through that cavity behind, if any moisture is trapped in there, it can dry out because of the airflow. And what the cool thing about rain screen skins is, because your insulation and your your membranes are doing, the majority of the heavy lifting in terms of thermal performance and waterproofing. It gives the designers a lot more flexibility to create what they want on the skin. Really, it's just the skin protecting, the elements that are doing the heavy lifting. So you can use a lot more profiles and materials there. And just keep that image of this slide in mind as I go to the next one. And I just wanted to just briefly talk about the thermal benefit of a rain screen. So as you can see there, you got the sun beating down on a hot day, for example, sun beating down on the facade skin. It's then heating the air within the cavity. Hot air obviously rises, and it's wanting to vent out the top. As it's doing that, it's drawing in the cooler air through the base detail, and that's helping to cool the entire cavity. And on a cold day, you won't get that rising hot air. So the air will be stagnant inside the cavity, and that will sort of create a buffer and help to contain that warmth within the building. And key benefit there really is the more constant temperature your structure is, whether it's steel or concrete, the less it's going to move, and it's going to have a lot of benefits, and less cracking in your buildings and all that. So that, I think, concludes what I was going to say today. Blake, back to you.
Yeah, awesome. Thank you so much, Dave. And so those are some quite basic but quite key concepts that I think it's really good we kind of encapsulate and just set the scene. And with that, I think I'll pass over to you, Alex. I'll invite you to the stage.
Thanks, Blake. Welcome, everyone. Thank you for taking the time out to see our presentation, and we'll just get started shortly. So today we're going to cover a few different topics, starting with 2019 NCC and the key changes in that code. We're also going to be looking at steel frames and thermal bridging. So in that steel frames, we're going to look at 3 actual wall build-ups. So we're going to run through a bridged one, so something without a thermal bridge included, as well as one with a thermal break installed. We're going to look at externally insulated, then we're going to move into concrete wall build-ups, both internally insulated and externally insulated. So let's get started first with the NCC, and we all know 2019, there came some big changes, and a lot of those went into section J 1.5 for those who know it. Now it's the one-stop shop for glazing and wall performance requirements. So in section J 1.5, it's going to look at the minimum performance requirements for wall and glazing, and for those components are now defined as wall glazing, the construction and methods needed to illustrate compliance against them. So for instance, AS NZS 4859.2, there's a 2018 revision. So by definition, your components are now considered as wall glazing. That's going to include your walls and your windows. So what does that mean for thermal performance? Well, increase in glazing now equates to a decrease in the overall wall glazing's thermal performance. So we're going to be spending a lot more money in actually compensating for that performance. So yeah, we're going to see more heavy-duty systems with regards to double, triple glazed windows to compensate, along with better insulated walls. So let's look at situations where we might have walls that are less than 80% of the wall glazing construction. We get a minimum total R value requirement. So this is for all climate zones and building classes of R1. Now that might seem low, but we'll see later that the R1 is actually hard to get. So given that a lot of the spandrels in these sections will not meet that R1 without being thermally broken. So this is going to be a huge game changer, guys. So and I'll explain as we go how this has been the case. So the other way we can look at this, in situations where you have walls, more wall, so 80% wall area or less. So those minimum performance requirements are going to be variable depending on the climate zone and building class. So again, 2019 definition now includes the thermal bridging, right? So I'll give you a quick example. In all climate zones, we're going to exclude Darwin. So in class 2, in your common areas, right up to 9A, other than the ward areas, we now have a minimum total R value of 1.4. This is for both windows and so the total wall, including the 2, right? So now 1.4 R value doesn't sound that much when compared to 2016 standards. However, recent changes in the in 4859.2 and the way 2019 looks at those have altered the way that we test building products for their and get to the R value calculations on wall build-ups. So we'll cover that today and through the 5 walls that we're going to actually compare against. So a bit about steel frames. Now, due to steel frames, and David covered a lot of this, being made of highly conductive material, so very poor in resistance, we expect heat loss. So from the inside, that heat that we're trying to maintain at a regular temperature is lost through the frame. And what we're trying to do is stop that from getting to the exposed exterior elements. So the best way to do this is to actually insulate external to the actual studs themselves. So as you can see this image, we have our internal insulation and a vapor permeable membrane, but we've also added exterior insulation. Now this is continuous. And how do we achieve this? We install a framing system like our envelope framing system seen here, where it actually has a very small amount of footprint touching back to the substructure, allowing for the insulation to be encased around it. What it also does is cantilevers the cladding zone outward from the insulation, allowing for a strong mechanical connection back through to the substrate. So we're using the insulation to do its job, and that is just to insulate. It also creates a ventilated cavity, which deals with condensation. In addition to this, what we try to tell people to avoid is using the insulation as a structural component. We've seen situations where they're using it almost like a packer and bolting substrates through the insulation. Ideally, we would like to see the load being transferred directly through to the slab through some form of structure. Other strategies include thermal break strips. So similar to our Vulcan wall, it's a non-combustible thermal break. You can place that on the exterior face of the stud, and it acts as a batten supporting the cladding. These can be both applied vertically and horizontally, and you get significant uplift in your R values and the overall wall performance by installing these. We're going to actually cover this later on. However, if you're going through a DTS solution, in section J0, particularly J0.5, which covers wall thermal breaks, the minimum R value is 0.2 that you need to achieve. So something like this, I believe, is a 0.27, so slightly above the minimum recommended. However, if you're going down the path of performance solution, thermal breaks are not required. However, when you start looking into the calculations for particularly around highly glazed highly glazed buildings, or if you're using steel studs, when you start to model this, you'll find that you actually do need the thermal breaks, and unfortunately, you'll have to install them anyway. Well, fortunately for us. So let's. What we're going to do is, there's 5 wall build-ups that I really want to touch on today, and I guess to do this, we need the assistance of, and I'm calling on Speckle, which is an online modeling platform. Now, for those of you who don't know this, what it does, it's designed to simulate both thermal and condensation performance of building elements, and it groups them all together. It does a lot more than that. It also can compare window to wall ratios and look at the overall building performance. It takes into consideration thermal bridging and AS/NZS 4859.2 in the 2018 revision. So if you haven't seen it, I highly suggest checking out Speckle and becoming a member. We also have a free portal on our website that sort of encases our own wall build-ups that we've put together. There are all other brands out there and even generic, so feel free to check that out. So let's get started with wall build-ups. We're starting with wall build-up 1, very common wall that we see. And what we're going to do is look at it against 2019, and we're also going to compare it against the 2016. So I'll just get started on the elements included here. So starting from the inside, your internal wall lining. We've actually also included, just to boost performance, it's a variable diffusion vapor retarder, which is called our Proctor Passive Smart VAP. What that does is actually stops humidity from getting into the wall buildup. So again, dealing with condensation risk. We have our 90mm stud here with bulk fiber insulation installed, a vapor permeable membrane, a vertical batten to create a vented cavity for your cladding. So looking at this wall buildup, now what we've done is we've looked at building class 2. So let's look at a multi-level residential building in climate zone 6, which would cover Melbourne, CBD, as well as Sydney. And you can clearly see here that we only really achieve an R value of 1.29. So we're not getting to the 1.4 minimum required, as I mentioned earlier on for these zones. Now, the interesting thing here is when we look against 2016 NCC, where we were looking at different ways of calculating R values, this would have been a 2.83 wall, and it would have passed 2016 standards. So the changes to the 2019 NCC, as well as the 4859 code, has really seen a massive shift in how these R values are looked at. So unfortunately, you will not be able to use this wall in this application. So what we're doing now is we're taking the same wall, and this is wall build-up number 2, and we've replaced the vertical battens with the Vulcan wall non-combustible thermal break strips. So by doing that, and you can see that here, we haven't increased the wall size in any way. We've literally just replaced one element that was probably a low-performing element, which was creating a bridge, and replacing that with a thermal break. So clearly here with massive uplift in R value. We've gone from what we had before, which was 1.27 to 1.97. Now it's surpassed the 1.4 minimum required for that wall. So great result. And you will see here almost a complete R value difference when compared to 2016 NCC requirements. We're going to up the ante a little bit now, and we're going to look at probably a slightly more advanced way of working with increasing R values and externally insulating. So this is, I guess, where I see, and we are seeing a lot more of this out in industry now, particularly in different climate zones and different building classes, which I'll cover off in a minute. So this wall build-up, starting from the inside, again, our plasterboard, and you have your typical 90mm stud insulation, vapor permeable membrane, of course, but we're now added a system which is a cantilever, like a helping hand system, like our envelope. This is our NV3. What it's doing, it's producing a cavity large enough for us to install continuous insulation. It creates a ventilated pathway for air to run through that for drying potential. And we've also allowed mechanically fixes and the cladding itself. So looking at the performance here, again, significant boost in R value because we are adding additional 50mm insulation. So we're doing a great result here. However, these sort of systems are more prone to areas where you might need additional R value. So where we have in class 2, we have a 1.4 minimum in this climate zone. What we've done, I've now modeled this on, say, a class 9C building, which would be an aged care facility in Melbourne. And you've gone from a 1.4 minimum requirement right up to a 2.8. So now even the previous wall I showed you would struggle in this situation. So what we do in industry right now is we're actually, the first thing we look at is, oh, gee, we need a higher R value. Let's increase the stud size to get more insulation in there. And what that does is incurs a significant cost to the overall system performance. Now, what we can do is just look at it a bit differently by installing insulation now within the external cavity with using the right systems. We've now done a few additional things. We've eliminated that, well, we've heavily reduced, I should say, the thermal bridge, because we're now, that stud, which is causing that bridge, is now completely covered with insulation. The other advantage is the structure itself is maintained at internal temperature. So as David mentioned earlier, we're trying to keep that internal temperature of our occupancy areas of about 21 to 23 degrees, and maintaining that all year round, no matter what's happening outside. So it's great for the structure and things moving around. But where the big plus here is, what we've done is we've moved the dew point. Where would if you were internally insulating, your dew point would be expected behind the vapor permeable membrane. So that's where we rely on the permeability of that membrane to actually allow for drying potential outwards. So when we do have that dew point in those colder months, where the insulation might get wet, then the permeability allows it to dry out. But in this case, the actual dew point has been shifted to the external cavity. So it's no longer in the occupied space where we live. It's now in an external cavity where it's subjected to ventilation and a lot of drying potential. So a lot healthier, and you'll see here is a very minimal risk of condensation forming. So that's a big take home for this one. So moving away from steel, I'm gonna start moving into concrete, and we see a lot of this in New South Wales, probably less in Victoria. However, this wall is one of my favourite walls, and all for the wrong reasons, and I'll explain soon what that means. And I'll just run through the wall build up here. So we have plasterboard on the inside, or internal wall lining of sorts. A 90mm stud, or could be larger depending on our value, bulk fibre insulation, and this is hard up against the concrete wall. So we're using the concrete wall itself as the actual rain screen, or the actual rain screen, the actual facade, so to speak. So we're literally painting it, rendering it, and you've got a flat surface, so why not? However, when we look at this as in terms of performance, we see a lot of red here. So, you know, it almost looks like my Year 6 English assessment, where we've got, you know, a lot of red tape here, a lot of red markings. So it's not thermally not going to get there because you're expecting this huge loss running through the system here. Because as we know, concrete inherently has very, very poor thermal resistance. Okay, so by insulating here, the other thing we have is a massive condensation risk, where again, dew point is where the cold surface. So if we're talking about cold, that cold is going to radiate through, and we're going to expect the dew point where we're going to have condensation forming on the inside of that wall. Now that water has nowhere to go. We've got 150 to 200 millimeters of concrete for it to permeate through. And it's just not going to happen. So it's going to take a very, very long time. Then you're subjected to mold growth, and it's an absolute nightmare. So to add the theatrics, here at DCTech, we call this the wall of death for a lot of reasons. It is ultimately a health risk, which is going to lead me to wall number 5, and this is what I call the perfect wall. It's essentially the wall of death, and we've turned it on its head. So I'm just going to run through this one quickly, where we have our internal wall lining and some form of battening to create services access. We have our concrete structure, a vapor permeable membrane. This is a self-adhesive that we sell into industry called Proctor Passive RSIT. Oh, sorry, Rack Type IC. Sorry, and this itself is completely self-adhesive, meaning that there are no mechanical fixings back to the substrate. also used in CLT applications. We are externally insulating here, and we're putting in our envelope framing that's allowing for this cantilevered framing and a ventilated cavity. With this system, the condensation risk is completely gone. We're getting to the R values that we need. Again, in this case, it was class 2, so we didn't need to go as high as this. However, I'm going to up the ante again and look at it in a class 9C building. And again, by beefing up the insulation slightly, we're right up to 2.86 over the 2.8. And again, by adding more insulation, we're just going to further be performing, further increasing the performance of that wall. In saying that, what we've also done here is keeping that concrete at close to internal temperature. So maintaining it at a constant temperature. So it's not moving throughout the day and throughout seasons. The actual concrete structure is now staying quite at the same temperature. So the other thing we're doing here is we're going to be taking advantage of the thermal mass effect. So a thermal mass, what does that mean? And so concrete we're going to start using its density. So because it's such a dense product, what happens is as we heat our internal wall, our internal spaces, it's actually charging up that concrete structure almost like a battery. So it's storing energy, storing that heat, or as we're heating or cooling the room. So what that's actually doing is that's giving back. So in situations where we're not using heating or cooling devices, might be at work, well, the wall is doing the work for you. So it's maintaining that temperature internally for a longer period of time. So you're reducing the amount of time you actually have your air conditioning or heating working. So reducing the actual energy output or input, into the building. So that's going to leave me with my actual takeaway for today. And it's going to be like, please, when you're looking at buildings, think outside the box, because that's where the insulation really should be. And, thank you for the opportunity, everyone. And I look forward to your questions.
Yeah, awesome. Thank you so much, Alex. It's quite interesting to see, that's quite a significant change incorporating glazing into the R value in between 2016 and 2019 NCC. So it's quite a dramatic shift.
Absolutely. Yeah, it's made a huge impact to the way we're actually building at the moment.
Yeah, definitely. And it's probably a more, you need to look at holistically in regards to the building envelope. It's probably a more accurate method of measurement. Definitely.
And again, when you look at window to wall ratios, I've modeled some of this externally. We couldn't cover it today, but the situations in class 9C buildings, even with the high performance wall, where you're down to like 11% areas that you're allowed to have actual windows. So you really got to look at the performance of the windows as well. So it's not just about the cladding, but you're right, holistic. We're going to be looking at this holistically now.
Definitely. Just before I throw it over to John, just remember, guys, if you've got any questions, please don't hesitate to throw those in the tab, and we'll get to those at the end. But I'll now invite John onto stage.
Thank you. Hopefully you've got the right screen there. Let me know if you've only got some notes in the bottom. So thanks for the opportunity. I'm John Davies. I work for a company called Oculus. We're based in Auckland, or we've got a few spots around the country. In New Zealand, if you haven't heard of New Zealand, we're a newly formed dictatorship, hiding just fairly close to you guys. We're a bit over the whole lockdown thing, and I think most people are watching reruns of Les Mis to figure out how to run a revolution successfully. But look, Oculus Architectural Engineering, we take the principles of physics and we apply them to buildings. We work with architects to ensure the building envelope meets building code requirements. For us, that looks like assessment of designs. It looks like understanding the constraints, proving compliance through to consenting authorities. And then we work on site with the construction team. So we monitor the construction, we test facades, and we sign off on successful completion of that design. It's a similar kind of approach to a Clerk of Works, which both New Zealand and Australia dropped in the 1980s. So sucking the life out of insulation. There was a claim last week that Australian homes are easily the most poorly constructed in all of the modern world. Your Jason York, he reckons Aussie homes are worse than Kiwi homes. Well, I call on that, I call bollocks. But then I got talking with some of my colleagues who agreed. So let's be generous and call it a tie. What we know is our houses are not good for our health. And so putting aside the key elements of heating and airtightness and ventilation, I'm focusing, like we all are in this series of presentations, on the way that heat moves through walls and how to improve what we're doing. By the way, we have the same challenge of housing built before current standards. It's a bit of a truism, really, isn't it? As soon as you improve standards, everything is out of date again. So what should we be doing and why? Well, the landscape we're all working in it is the same. I know it's tempting to add solar panels, water tanks, grey water systems. They're visible, they're tangible, they are save the planet types of things. But I think the real change is in sorting out how energy hungry the building is. Now, there's a challenge here because you end up trying to sell a reduction of something, and there's some strange psychology around trying to sell something which is not there. But on the positive, we know what it is to be comfortable, and that is something you can sell. So insulation allows comfort at lower energy demand. So you'll have clients who can afford enormous power bills to be comfortable, but that's really becoming as socially acceptable as driving a Hummer when you could have chosen a Tesla. The comfort can be there in both, but one of them costs a lot more to run. So Australasian timber houses, new and old, are fundamentally the same. We have framework and we have insulation squished between. This is chopped and stopped insulation. It's chopped into pieces and it's stopped and started by the framework of the wall. So what I'm going to cover now are the effects of, and we've covered this already with what Alex and David have touched on, but I'm going to show you this in some graphic forms using a software called Therm. And we're going to look at the effects of that framework on the heat transfer, figure out, nail down, make sure we all understand the why and why we should look at some other solutions. And as we get into that, I'm going to take a slightly wider path from what Alex has done and look beyond the solutions that we have into some new things that we're exploring here at Oculus 2. So simply put, timber frame here at 600 centres, so 140 frame, partially insulated, which is not something we recommend, but this is just for the graphics. So the reason that we don't recommend partially filling a framing depth is because of the convective air movements that can occur through that cavity. So in this case, just to be super clear, the colour is the temperature. So inside the building at the top, in this case is 20 degrees and outside is 0. But the principle here is exactly the same if you've got 40 degrees outside and you want 20 inside. The idea here, and I think David touched on it, and certainly Alex too, that heat is going from hot to cold. It's not the other way around. So heat is always to try and warm up the cold area, whether that's in conduction, whether that's in the radiation or convection. So the value of the wall here is about 70% of the sticker R value, meaning what's stamped on the bag when it arrives on site. It's called effective insulation or construction R value, as Alex has touched on. It's the value of the insulation after you've subtracted the missing insulation. But it doesn't stop there. It's totally related to the conductivity of the frame itself. And so the numbers, again, I'm going to repeat this. So the timber has a conductivity, and our pine that we use generally has a conductivity of 0.12 watts per meter Kelvin, and fluffy insulation has 0.04. So that's about 3 times, and I know the data on the screen before said 4 times, but I'm calling this 3 times faster heat transfer through the timber frame itself. And it's shown here by the curving of those lines of the color into the timber. So the amount of frame becomes really important. We thought until this year that we had on average about 18% of timber as opposed to insulation in a typical wall. Well, it turns out through the research that was done that it's 34% on average, with anything up to 50%. And then we jump into the steel frame, which we've seen on screen a couple of times, this time with this thermal modeling showing how the temperatures are actually changing around that steel. So this is what I'd call wild lines of temperature gradients. The heat is being transferred really fast through the steel, as we've already seen, but it's only 1 millimeter of steel. I mean, how bad can it be? Well, we know it's bad. We had it on screen earlier, 1,300 times difference in the heat transfer through that steel. And the challenges, I'm just going to go back to that, the challenges don't just stop by stuffing more insulation in the wall. The condensation point, the dew point in that construction is still going to be much closer into the inside of the building in cold conditions than it is also on the steel. It's going to be much more chance of condensation forming on that steel further in towards the inner side of that building. So there's some challenges there, but if you apply the principles of heat transfer and start to get your head around the idea of a condensation or dew point temperature, it's going to be pretty useful for your design. And so the best answer, as Alex has shown, is to put all of the insulation outside the line of framing. At this point, the lines of temperature in this image remain parallel. At this point also, the framing material becomes irrelevant. So it could be CLT, it could be precast concrete, it could be steel. So now we have to attach cladding structurally outside this insulation. And it's at this point that it's really easy to start destroying all of our good work. So the first option here, and I've taken this from a Canadian company called RDH, who do some research in this space, a lot of research in this space. So this is the first and the worst, and it really takes us back to square one again of having all of our insulation chopped and stopped by either timber or steel, in this case steel. So we have framing to the right or the back of the image, we have yellow plasterboard sheathing, and we have a weather tightness layer, then insulation that looks like a rigid board, then the cavity, and then a cladding. So the problem is the big piece of steel through the middle of the insulation. That is the thermal bridge. Then, as Alex has covered, we looked at an intermittent connection for that structure, or sorry, for the cladding onto the structure. And this, RDH have estimated this, the thermal performance of this is dependent on a whole bunch of stuff, but between 40 and 70%. So we've already covered it. Aluminium, we know, is the 5th best metal at conducting heat. So if you're going to use it, break it up. And the same goes for windows and the window performance here. Remove the contact surfaces from each other, which means use thermal breaks. Use thermal breaks both on the vertical and in this case on the horizontal, whether my cursor will sit on that screen, but between the clip, between the elements of the clip, the units can be broken up. The connection from aluminium to aluminium can be broken up. So the point here is the material is good, but you've got to carefully consider the position and the connections. And there are some options in the market, both in Australia and New Zealand for this. So this is the Technoform isolator clip. It's an intermittent connection, but it's shown here as a black polyamide with an aluminium top hat. So this doesn't have aluminium all the way through from front to back. A rail is attached outside the insulation line. The insulation compressive strength is not important, unlike the following one that I'm going to show you. Lightweight, fluffy insulation, as is shown here with the earthwall product on the left, is possible. Thermal performance is pretty good, with low thermal conductivity. So the polyamide black element of this is the same plastic unit that is used within thermally broken windows, and even the edge spaces between the glass units on double glazing and triple glazing units. Fire performance is pretty good, especially with the use of rock wool. That's been proven through some NFPA 285 testing as well. And the final cladding attachment type is simply a long screw through a batten. Now, you've got to understand some of the limitations here. As you have heavier and heavier cladding, and I'm not talking about brick, because brick would be, the load transfer would be treated differently, but the limitations become some of the weight of the cladding, some of the wind loading as well. But this is an area we've been working on for almost 3 years now. Again, image here from RDH in Canada. There is care required, but the outcomes thermally are really good. So the compressive strength of the insulation is really important. The grades of your substrate, in this case steel, are really important too. So what are you fixing back through into? So we've done a bunch of mock-ups with this. In this case, a steel frame with a plasterboard sheathing, a weather tightness layer, rock wool, steel batten, and then cladding. This is 100 kilograms per cubic meter density of that rock wool. So that's pretty important because you're creating a truss effect to carry the cladding dead weight. And if that gets wet, so if we, as we've talked about today with the rainscreen cladding approach, where you can get some water through the cladding system and back to that next layer, if it does get wet, well, it's rock. It's spun basalt, candy floss basalt. Bugs don't eat it. Fire doesn't eat it either. Getting into that same or similar mock-up, the window position here becomes quite flexible. So here the window is recessed into the timber frame, but the thermal performance improves when the window is in line with the insulation. Now, when we discussed this a few days ago, what we're going to present, I was asked to do a little bit of a touch on what I've been looking at over the last couple of years with a Master of Architecture project. So I'm going to touch on that now. Hopefully it will create some questions and we'll be able to answer some of those now. So what I have looked at is an existing wall. So my research in this, well, I've got it in our test booth here. I've looked at existing walls, existing timber weatherboard walls from the 1940s to 60s, which is super common in New Zealand with our existing housing. I've looked at improving those thermally from the outside. And the intent there has been to maintain the occupancy of that building. So it was initially targeted at social housing. And then the realization is that actually an awful lot of our houses are like this, and we don't have the luxury of the disruption and cost, and just, yeah, not considering those things. So I'm just going to run that. So this is just showing, it's more important here on the left, the air leakiness of this wall around the windows, through the weatherboards. And then if you can imagine, and that's just the fan ramping up in the background there. It's going to finish. So if you could imagine what I'm going to do with this wall and what I've done to the outside is to stop the air leakiness first and to add some insulation. So everything is done from the outside and onto the outside. The project was called the Parker Wrap. You can see in the image there, timber weatherboard wall existing, and then we're overlaying. So there's a replacement of window here, and then we're overlaying weather tightness layers and the dotted line, thermal insulation, cavity, and new cladding. All of that fixed back through to the existing structure using long screws through insulation. This is the wall in practice after I had sort of done all of the testing with wind and water and seismic in our test rig, and then started to strip that wall back again for some video work that we were doing. So what you're looking at there is the hidden weatherboards, now down to the bottom right where I've exposed them again, but everything is an overlaying process. So the reduction of waste is quite significant, and the reduction of disruption to tenants has been quite a significant part of that process, part of the driver there. Rock wall insulation, non-combustible batten, timber charred cladding there, so that's very combustible, but yeah, just for the mock-up. So when it was still in the test rig, did a whole lot of testing for wind and water and seismic on that, and looking at the drainage planes, looking at where water can get to and what sort of weather tightness performance we could get out of it. So if you'd like to know a bit more about that, that thesis has only just been submitted in the last few weeks. So there's a bit of, I've got to defend that thesis yet and then write up some design guidance. But otherwise, Oculus, as our company, we're involved with a bunch of stuff across New Zealand and a little bit in Australia, across new and existing buildings, and love to hear from you and love to hear some of your questions right now.
Awesome. Thank you so much, John. I've got a real quick question. So it's the approach of cladding over the face of that existing facade. Is it like it makes a lot of sense, because often when you pull the facade off, you get into that cavity, there can be all kinds of issues. But if you're cladding over the face, do you replace the windows so that they sit in line with the new cladding? Yeah,
so that's a replacement window in that image there. Shelby Wright Test Labs is actually our little company that we've got alongside Oculus, so if there's any confusion there. So yeah, what you're looking at there is the existing 1940s mock-up wall, but with that window replaced, and I've got that on a back dam. So if I just jump forward, I've got one image of that, which I hope is somewhat clear. So there's either a subframe that you would put into the window opening and as a new window opening, or you would use a back dam, and that's the piece of bent aluminium or steel there, but that's still inside the thermal line, so you're not actually breaking up. So that's a thermally broken window. You're not breaking up the thermal line on that insulation as that insulation comes around a window. So much more detail in there if required, but that sort of shows you the line of the double glazing unit. When that's in line with the insulation, the performance is pretty good thermally.
Yeah, interesting. Thank you. Thanks for sharing some of that research. We've got a few questions coming through, so if anyone does have those, please throw them there. I'll just really quickly, today is a CPD presentation, so there will be a survey that comes out as well. So I'll just quickly cap through some of the questions that you'll be answering as part of the CPD. The first one is, name one advantage of using a rain screen in your facade, and there's quite a few different advantages. It's quite practical and pragmatic. The rain screen skin will take care of the aesthetic considerations, so you can do the bulk of the thermal performance and weatherproofing and whatnot in behind it. So it's quite pragmatic. It's also very durable. It's a low maintenance and it's solution, and it's quite energy efficient as well. So that's question number one. Question number two is, name one addition to a building envelope that will improve thermal performance. And both John and Alex have capped off a few of those today. That's today's whole presentation has been about that. So it's all about breaking up that thermal bridge. So you can add a break strip, you can extend out the insulation, and you need to address how the materials are all coming together and where the thermal bridging is occurring. And then the last question is, how does improved thermal performance impact on operational carbon? And Dave talked about this a little bit at the start, but I think the biggest thing to recognize these days is we need to be more energy efficient in our building designs, and thermal performance is all about improving energy efficiency within a building. So that's in reducing the operational carbon required for in the building infrastructure, and the number one way you do that is through thermal performance. So that's it for the CPD questions. There will be an email that will come out straight after this if you would like to answer those and get your CPD point. I'll just now go over to a few questions. And the first one, I believe, is directed at you, Alex. It's from Michael, and it's, if I've got an external wall with 150 mil deep stud and 80 mil of insulation, am I better to keep the insulation towards the external side of the stud or the internal side?
Yeah, I think actually that was probably better directed to John because he covered that in his presentation. John, did you want to cover that one off?
Yeah, look, first and foremost on that, what we always recommend is filling all of the depth of the cavity. So there's a couple of reasons there. One is the fluffy insulation is a very cheap by square meter element, and two, more importantly, the leaving cavities on either side or around blocks of insulation really degrade performance. Like there's some significant, even a few millimeters of gap around around any of the 6 sides of a piece of insulation degrade its performance quite significantly. So that'll be first. And in actual answer to your question, if it's a must do, I think you should put your insulation to the outer edge. It would be better to be out at the weather tightness line than it would be toward the inside, and for the similar reasons of having a bunch of complex, ways in which moisture will transfer through that system or through that assembly if you leave a big gap between insulation and a weather tightness product. So, but you can model that. You can figure out some of that stuff. It's a little bit tricky to model.
You can run that, I think, on Speckle itself. There's if you can model that in Speckle, and it gives you the option to flick it from the internal face of that wall of the stud, let's call it, to the outside, and try that and see if there makes any difference. So I know the guys who developed that have gone, they're pretty clever guys, so I'm sure they've thought about it. So I suggest giving it a try.
That Speckle tool seems super handy. I think it probably speed up quite a lot of calculations.
Yeah, it definitely does. We've shifted to that for our quick steady state analysis. We're finding it's quite useful.
The next question is, if I have a steel hollow section in an external wall with no room either side for insulation, is it worth blowing insulation into the cavity of that SHS?
Not really, because you're actually now got 2 pathways. So ideally you want to insulate on the outside of that RHS section. So it's creating that bridge. It's no different to a steel stud. It's insulation inside. It's not really going to do much.
There's one radical solution there, and that is to heat that element. So it's done a little bit. I've never seen that done here, but it's done a little bit in North America where they heat frames of windows to avoid condensation. So it's a throwaway energy, but it avoids condensation forming on that element.
Interesting.
Radical.
Yeah. We have a question going back, Alex, to when you were exploring the different wall types. And in particular, you went from talking about the wall of depth with concrete and then kind of the solution to the wall of depth where you had the insulation sitting on the face of the concrete. I think the question comes from talking about the wall of depth earlier with the moisture getting into the concrete. And the question is, what if in wall number 5, where you have the external insulation, what happens? Can moisture get into that concrete?
So we think of moisture. Okay, so we've got a ventilated cavity on the outside of that. So what we're trying to do here is, depending on what insulation you're using. So if you're using, say, like our Vulcan wall, where it's an 80 kg density, but it's also hydrophobic. So it's designed for that application where water is just going to naturally want to be resistant to that. However, even if water does get through the cladding, or just merely by condensation forming, you have a ventilated cavity there, meaning that you're going to get that natural convection happening for drying out potential. So even if it does get wet, I understand there'll be a reduction in temporary reduction in R value or performance. However, that'll dry up very quickly.
Yeah, thanks, Alex. The next question is directed at you, Dave. So it's, how do you integrate Click-on Cladding with some of the wall types discussed?
Yeah, okay, good question. Yeah, so we have worked through a few details with Alex at DCTech and how do we integrate with that envelope system. if you jump on our website, if you go to the Click-on Cladding page and over to the tech specs page, there is a few diagrams of how to integrate that, which may help. We do have a brand new white paper coming out. I think it's next week, and we'll be emailing that out. So that'll focus just particularly on this integration of our system, where you get all the benefits of the different looks, and integrating it with these thermally broken systems like DCTechs have. Does that answer the question?
Yeah, it does. Thanks, Dave. We do. So yeah, just to recap, so there'll be an immediate email that'll come out today for CPD questions and a replay of today's presentation, but we've also been working quite heavily on a thermal performance white paper, which we'll send out in about a week. But that ties into a question you answered online, Alex, from Eleanor, in relation to when we talk about all these different build outs, integration of services and windows and whatnot are also play an integral role. So that kind of stuff Alex mentioned is available on his website. We've got, which is the DCTech website, and we've got some details on ours as well, because that's always critical, and it's a very case by case basis. We've only got time for probably 2 more questions. So the next one I'll ask is, the dew point location within a wall build out appears to be critical to its performance. Is there an easy means for architects to work this out easily when designing walls and build out?
Yeah, I'm going to say yes, it is quite easy. One of those is you can hand calculate, which is, it's not guesswork. You just need to know where the temperature is and what the humidity of that air is. Now, can you do that on your own? Yes. Otherwise, get one of the apps. You can download them on your phone. If you just search dew point calculation as an app or in the App Store, you'll get some of those. I think before, the danger there, you grab a calculator, and what you need to know is how to apply the information that you get. One thing we do know is, and I think Alex touched on this a little bit, that insulation generally will have the dew point about the middle of the insulation. So that's just a really, really rough rule of thumb for winter conditions, 20 degrees inside, 5 or 0 outside, 50% humidity. The dew point temperature is between halfway through the wall and 2/3 of the way through the wall. Super rough here. The point there is that, as Alex said, if you put the insulation outside your weather tightness line, condensation that does start to form in that insulation is outside the weather tightness line. And it's a similar principle to what I've used with where I've put it's not different at all. So my research has just looked at retrofitting. Same insulation outside, but it's outside the weather tightness line. And what's key there is it doesn't matter how much insulation you add, the dew point temperature is still about 2/3 of the way through toward the outside. So you can never move it outside the building. It's just a physical impossibility. It's always going to be at some point within the insulation. Now, one key thing here is that even if there's a dew point temperature in the middle of a wall, if you prevent moisture from getting to that dew point temperature, you don't get condensation there because there's no moisture there. So what we're trying to do is get that balance of understanding how heat moves through, and heat or moisture goes where heat flows. So heat drives moisture with it. And it's just a combination of slowing down moisture movement, preventing it getting to a dew point. But the danger here is trapping. You can't just put plastic sheets of things on fluffy insulation because you prevent drying. So we still want to allow some drying capacity in the wall. And if you think about it really simply, you've got a wall structure. If you put moisture in, you want less moisture in than you can get back out. Either way, inside to outside, doesn't matter which way, both ways, good. Put a little bit in, but get more out. And then you end up with a dry structure and a durable structure. And the durability is the same whether you're talking about timber or concrete or steel. They all have degradation pathways related to moisture.
We'll just finish up with one final question. the question is, does the orientation of the wall impact on its thermal performance? And has this been modeled as a percentage difference between orientations?
Who wants to answer that? My answer would be no, but for a different, well, maybe a reason. But
well, if you talk about orientation, if you flip a wall onto its side, it's a roof. Same would apply.
So it doesn't change the thermal, but it does change the way that moisture moves through, because moisture goes where heat flows.
Yeah, interesting. Thank you so much for all three of your time today, Alex, David, and John. I think it's been an incredibly interesting presentation, and thank you to all of our attendees for spending some time with us today. I know we went a little bit longer than originally intended, but thank you very much for sticking around. There will be a replay that we'll send out after this. If you are interested in the CPD points, there's also a survey. You fill that out and we'll reply with a CPD point. Other than that, thank you very much, guys. Hope you enjoyed it.
Thanks.